We're going to go through these review problems together. I'm going to give you guys like about a minute just to write down the givens every problem to start with. So go ahead, read the first one. Write down any givens on your own for every problem. Okay, I'm going to give you 1 minute. Go ahead.
Slow down or speed racer?
Come on, I'm trying to make you think like it's a test. A lot of you don't work at this pace, you know?
A lot of you don't work at this pace. Yeah, Mr. Howell, what's it under?
It's the last thing under documents and handouts.
Alright, cool.
The last file under documents and handouts.
Yeah.
10 seconds. Let's go through it. Alright, so a 2 centimeter thick bar of soap is floating on top of the water. If 1.5 centimeters of the soap is underwater, determine the density. It seems at first like this is impossible, to be honest. Because it's like, wait, I have nothing. I have a thickness of the soap and how much is underwater, right? I don't have volume. I don't have another dimension. I don't have mass. So it seems like you're kind of like, I don't know what to do to start. That's why I wanted to look at a problem like this. What do you actually know, though? There's one thing you do know.
The density.
Okay, the density of water, what is it?
1.
Okay, or 1,000. What table are you looking at? Because if it's in grams per cubic centimeter, it is 1.
Yeah, that's what I'm doing.
Okay.
Yeah, we always do 1 gram. We always do
Yeah, but we've done this for the last week, so you should have this by now, right?
I don't know where I've been for the last week.
I don't know where either. So the density of the fluid is given, absolutely. Absolutely. All right, what else?
A is 0.02 meters. A1 is 0.02. No, R1 is 0.02 meters.
There's a bar of soap. And you're given the thickness of the soap.
Mass, isn't that the mass?
Think about it. You're given the thickness of... Look, here's a bar of soap, right?
Diameter.
Okay? You're being given the thickness of the bar of soap. How is that R or A? Why would you use that variable? I'm just curious.
Area's length
Just asking. I'm serious.
Area's length times width.
Okay. Area's length times width. Good. But let's think about what we know relatively speaking. This is the bar of soap. Where's the water level up to?
1.5. 3/4 of the way.
What is it? Say it again. Hold on.
3/4.
3/4 of the way. That's the key. Take a look. The water level is here at 1.5 centimeters, which means that the water level is 3/4 of the way up the bar of soap. Agreed?
Yeah.
Everybody? So what I can say is the following. This is kind of the statement that you need to use intuition to make. You could say that the volume of the fluid displaced is equal to 3/4 of the volume of the object. Think about it before you say anything. Just think about it. The volume of the fluid displaced, VF, is 3/4 of the volume of the object itself. 1.5 over 2, just like Helen said. The rest of the shape doesn't change. It's the same throughout. So we could reduce that fraction of 1.5 over 2 to integer values of 3 over 4. Okay? So we don't have any numbers for the volume, but we do know that the amount of water that has been pushed aside is from this bottom piece of the soap, which is 1.5 out of 2, which is the whole piece of soap. So the volume of the fluid displaced is 3/4 of the actual number itself. Imagine you knew what these numbers were. Pick numbers for these two real quick. Pick easy numbers.
2 and 4.
All right, 2 and 4. What would the volume of the whole soap be? 2 times 2 times 4. What is it?
16.
Good, 16. But then do 2 times 4 times 1.5. What do you get when you do 2 times 4 times 1.5 to get the amount of water displaced?
12.
12. So what's 12 over 16 reduced to?
3 over 4.
So the amount of water displaced is 3/4 of the actual volume of the soap. That's this right here again. Okay? This relationship will help us solve this kind of a problem. All right.
VF is always going to be 3/4 of VO.
In this problem it is. In this problem it is. Yeah?
What's VO?
The volume of the object. We don't know these numbers, but we do know the values. We know that the water level is 3/4 of the way up. So 3/4 of the water level, or 3/4 of the object, is how much the water level is displacing by. Okay, the amount of water that's pushed aside. Hold on. Let me go into the next part, then I'll take a question.
How did you know 1.9?
The object is floating, so what do you know?
It's less dense than the water.
Okay, good. What else do you know about the forces?
They're like equal.
Good. That's it, Helen. Forces are equal. Remember, if this bar of soap is floating, the buoyant force must balance the gravitational force, or the weight. So we know that the buoyant force must equal the weight of the object. And we have formulas for both of these. Let's write them down. Formula for buoyant force, rho F, VF, G. We know VF in a sense, because we have VF equals 3/4 VO. We know rho F, we know G. What's the force of gravity always? MOG. MO for mass of the object. Okay, but we don't know the mass of the object. We don't know the mass of the object. What are we trying to figure out? What is the problem asking for? Of what? No. The object. The soap. The object. So let's replace M. Remember this formula. Density equals mass over volume. Solve for mass. You get mass equals density times volume. So take this quantity and plug it in here again. We've done this many times already now. So plug in rho V for M.
Are you really cold?
For those that are always hot in the room, it's kind of tough. So for those that aren't, maybe bring like a sweatshirt or a sweater. Okay? That is an option. You can wear something. Can't the girls wear something? So then wear a dress shirt and wear a sweater. And don't wear a polo. I don't know. I'm not trying to be mean, but I'm being honest. Because usually more people are hot in this room. That's why I allow the AC. I don't really care either way. But I'm just going by majority for the most part.
Yeah, that's nice. Run back to kindness.
Anyhow, this is where we're at right now. What are we trying to find? Here's what we're trying to find. Right here. Okay, we're trying to find rho 0. Okay, the density of the object. What can we cancel on each side?
Is that a 0 or an O? Gravity for the sun.
Object. O. Cancel gravity. Now, replace VF with the definition of VF from up here. That's what we said. The volume of the fluid displaced is 3/4 of the bar of soap. This is what allows us to solve this problem. Replace VF down here. Okay, replace this VF with 3/4 VO. Now what's on both sides of the equation? VO. And what happens coincidentally? Look at that. And we know the density of the fluid, so we can solve for this. What is the final answer of the relationship you can see? And this is kind of crazy to think about. Read this in words. Read what you see here. Helen.
PO
In words, Helen. In words. The density of the...
the density of the object is equal to...
Is
3/4
Of?
of the density of
The fluid.
the fluid.
Think about that. The density of the object turned out to be just 3/4 of the fluid.
So there
Which is exactly what...
relationship.
Yeah, that relationship from earlier where we had the VF equals 3/4 VO. So what we can say is this. If the bar of soap was submerged halfway, it would have
1/2
the density.
the density.
1/2 the density. You see the relationship there? The amount in proportion that the bar of soap was submerged was 3/4 of the actual bar, which means that the density is 3/4 of the actual fluid. There's a relationship there. It's a generalization that you can make. Okay? Go ahead and plug in. What's 3/4 of 1,000? Everybody. 750. But the key is to notice the relationship here. Okay? The key is to notice the relationship here, that it turns out to be the exact proportion of the amount of the object that is underwater. This is assuming the object is, I guess, isotropic. Meaning, sorry, I shouldn't even use that word. Let's say non-tapered. What does tapered mean? Tapered. T-A-P-E-R-E-D. Tapered.
Like messing around with the like.
I don't know if that's
Tampered.
tampered.
Oh, just kidding.
Okay. I don't know if you were thinking of a different definition.
The third.
Yes, something that is receding or getting smaller, like a baseball bat. The barrel is the thick part of the baseball bat, right? What about the handle? Isn't it thin? The baseball bat? That's called tapered, when the diameter gets smaller and smaller as you go down the axis of the cylinder. So an object like a cone is tapered. Is that clear? So like, you know, if you had like a fire hose, the firefighters come out to put fires, the hose looks like this. Here's the actual hose that follows the line, and here's the nozzle. It looks like a trapezoid, it's tapered. It gets narrower. Why would it get narrower, by the way? Why would it get narrower?
More force.
Not more force.
But it comes out faster.
Why? Because
Because less pressure. I mean, no. Yeah, less pressure is faster velocity, so there's less pressure at the top of the nozzle.
yeah, less pressure at the top of the nozzle, more pressure behind, so it increases the velocity. And this is also because of, remember, AV equals AV, the continuity equation.
Oh, yeah.
As the area reduces, the velocity increases. Okay? Both ways work, though. You could say both answers there. That's fine. Okay? Let's go to the second problem. The first two problems in this packet are the toughest, I'm telling you now. The last like 5 or 6 are not that tough. This one is very tough. That's why I left you a lot of room. There's going to be a lot of work. Yeah, this next one is tough. Go ahead and write down what you know as your givens. Go ahead. Read it for a minute. Write down what you know.
Row 1,000 kg over.
1,000
kg over
Meters cubed.
meters cubed. Nice and loud. Come
I
on.
hate you.
Now, that's the density of water. Relax. Relax. That's the density of water.
No, he's always like, what is he doing that?
That's a baby car.
No, she's responding because you were mocking her, obviously.
Exactly.
All right. What else do we know, Helen? One piece of information.
Oh, FG is equal to 315.
How do you know that?
It says an object weighs. Weight is Fg always. Force of gravity. Remember, those are synonymous. Force of gravity and weight. Somebody else. Somebody else. Hold on, I know you know. There's another piece of information. Steph, give me something.
With 265 newtons, the VO.
Not the VO. VO is volume. Those are newtons. Those are force, right? Newtons measure force.
So FO.
Not FO. Emmett, help her out.
FB.
Is it what?
The force of buoyancy.
It's not FB, but it's like FB. We're going to use it to find FB. Not FF. That's a force of friction. There's no friction here.
Yeah,
What is it?
interesting.
F net. F net. Very good. Remember, people, F net, write this down, is the apparent weight. F net is the apparent weight. You're told that it weighs 265 in water. That is the apparent weight in water. Because you weigh less in water, right? So I can start by writing F net water. And I need 2 subscripts here, which is annoying. Because I have another F net as well. Helen, what's the other F net?
Oh, wait, can I talk about FG?
Nope.
Oh, yeah. F net in the oil is 275.
Good. All right. Now, I know some of you saw it already, but think about the relationship from your free body diagram. Everybody think. Picture a free body diagram. You got a box.
FB.
FB is up, FG is down. Can everybody see that in their head?
Yeah.
So, acting up is FB, acting down is FG. Therefore, F net equals FB minus FG. This is something that is not given on your formula sheet. But this is something you have to know. Any object with buoyancy, assuming there's like no chains holding it down, like we did that example of, okay? The F net is always going to be FB minus FG. And we have the F nets in both scenarios. So what can we do in those scenarios?
Wait, you have a what?
We have the F nets when it's in water and when it's in oil. You see that? We have F net in water and in oil. Nicole, give me something.
Can you just like solve one of them by using one, like the oil F net minus the FG?
Okay, so what are you finding by doing that?
You're finding the FB.
FB of each. Very good. So watch what happens. Using this formula, whoops, let me box it in. Using this formula twice. Once for water, once for oil. Watch, we're gonna show. F net, when it's in water, is 265. But which way is the overall F net acting? Up or down? Is the object still being submerged in water, or is it floating at the top of water? It's submerged, right? It's submerged. So which way is the overall F net acting? Down. Here, let's look at the back of the problem. When immersed in water, submerged and immersed are the same word. Immersed, filled with, around. So the overall F net is acting down. And this FB is what we're going to look for in water. And this is minus the weight. What was the weight, people? The original weight. What is it? 315.
Don't you subtract the
Watch. Add the 315 over. What are you going to get, Helen?
315 minus 265.
Which is? Yeah.
Why is it negative? Why is there a negative sign?
No, because you added on both sides.
No, there's a negative sign. It's a negative 260.
Because remember, the object, the overall net force is acting down if it's being held down to the ground. Think about it for a second. Which is bigger if an object is immersed? Force of gravity or force of buoyancy?
Damn.
And gravity acts. So the net force has to be. Okay? On the other side, you have the same thing, but instead of water, now you have oil. Look at the weight in oil. It's 275, but it's acting down. So this is going to be negative 275. But it's the same process. It doesn't change. Sibylla.
Where are the tissues?
Do we ever have tissues, Sibylla? You're asking like there's tissues every day.
I feel like there's tissues.
There are never tissues.
Sandpaper.
There's always sandpaper towel right there. Tristan.
Can I go get?
You have to think outside the box. You have to say to yourself, what can you do with the apparent weight? If the object feels like it's 300 newtons, but it's really 350 newtons, where is the 50 newtons going to? That's the buoyant force. It's helping you when you're in the water. Think about when you're swimming. Doesn't the water help you stay up?
Yep.
That's that assistance. That's the deviation. If you normally weigh 315, but you only feel like you weigh 215, 100 newtons automatically, or 100 pounds, whatever, of buoyant force. That's the difference. That's what it is.
Always graded.
What's what? The buoyant force is less than the gravity force, gravitational force, because it's submerged in water. Submerged. It's equal to gravity if it's floating.
Yeah, FB will either be
Equal
greater
to
than
or
or less than or equal to.
No, it's not. It's not.
It's nasty. Yes, it is. That is a war.
It's been there forever. I used to
It's a skin tag. I have
And we cut our elbows. You know, both elbows.
How? Okay, yeah, that was a war. That's so rude.
Yeah.
Where did you? No, we're on that level.
I didn't
Okay,
know.
wait, what? The actual police. When you're warm, no, but say when you're in the pool, when you hold someone, they actually feel like 10 pounds.
Yeah. That's their apparent weight. That's that net.
So if someone weighs like 115 pounds,
They're getting 100 pounds of buoyant force.
they probably in real life.
Yeah.
It's
The buoyant
actually
force is.
100 pounds.
Yeah, because the density of us. We're not that far dense. Our density is not that far from water. Think about it.
So like it's almost your whole weight. Like what is there?
Yeah, it's almost holding.
Is there a percentage? Like
Of course.
85% or something?
It's the percentage usually of your actual density. Indifference.
Is that like a ratio?
No, I'm talking about like.
I know, but there's no answer. It depends on what you're in, Helen.
No.
Yes. Let's keep going. Next. So, those are two pieces. Listen, folks. Those are two pieces of information. Now, we want, what did part A ask for? Somebody read to me. We're going to have to use these two. That's not even, we're not even close to done, right? You can see that already?
No, wait. I thought
Okay.
we were so done with this.
No, read what it says. Find the what? Of the object.
Why are we searching?
So, let's write this down, people. Let's write this down. Remember this for the object first. This is where we start.
Are we almost done?
But we know that this is really equal to... Okay? That's what we know. We know the weight of the object. That's easy. We have that already, 315. We don't know the volume of the object. We want to know the density of the object, so we need to get the volume of the object. Again, ignore this formula in the middle because we're not using it here. Take a look at what we have left. We know this. We know this. We want to know this, so we need to know this first. We need to know the volume of this object when it's immersed. That's our goal. If we can find the volume of the object, we can find the density of the object as well. We don't have the numbers, so we have to start and think, what can we do with this? Yeah, but look, guys, stop talking and focus. Look up here. We have FG, we have G. We want this. We don't know this.
Wait, but don't you have row of
So we
water?
can't plug in yet. We're missing V0.
Mr. Howell,
Okay?
don't you have row of water?
Absolutely. 100% we do. So let's use it now. We don't have anything with this though. This is row of the object. This is not water.
Oh,
Okay? It's an object in water, and then scenario 2, an object in oil.
Oh, so do we need to find out the relationship of VO and VF? Oh, but we don't have VO.
We do. No, we do. That's exactly right, Erica. If an object is completely submerged, doesn't VO equal VF?
Yeah.
The object itself is the same thing as the amount of the fluid displaced when it's completely submerged. Let's find VF then, and we can plug it in here for VO. How do we find VF? What formula does that come up in? Emmett, I saw your hand before. Do you have the formula that has VF in it?
What's the VO equals VF? Are you saying
That we know, yes, but what formula for forces do we know?
is it V equals M over rho?
Yes, but we don't have mass in this problem, so use forces. Use forces. Which force formula has the volume of the fluid in the force formula?
FB.
There it is. Go ahead.
Don't we have mass? Because divided by gravity, or weight by gravity.
Sure. Yeah, that's fine. That's fine. You can find the mass. Fine. But then if you have the mass, we're not looking for the mass. We're looking for rho. That's why, Thomas. Yeah, we could find the mass. Sure. Emmett, keep going. FB, the force of buoyancy of, we're going to do water, right?
Yep.
We'll do water because we know the density of water. What's the formula here, Emmett?
That would equal rho F times G times V F.
Good. Well done. So, we have this formula here. Take a look and pause, please. We have this formula up here for the object. Sibel, pick your head up. We have this formula for the object up here. We're trying to find VO, but we can't find VO. So if we find VF here in this formula, it equals VO. But in the water, we know this. Why didn't I use the oil? Because we don't know the density of the oil. That's part B. If I used oil instead of water right now, we would not know this value. That's part B of this question. So we're using water because we know the density of water. We know G. We know the force of buoyancy of the water. We can find VF. So Helen, what do you get when you solve for VF?
I have a question.
Solve for VF.
I didn't do that.
Do it.
VF equals FB over rho F G.
Good. What's your question now?
Okay. So in the last
Plug in numbers.
equation, where we got the rho is equal to like the rho of the object is equal to 3/4 rho of the.
Yes.
Okay. Couldn't we do that like proportionally in this one? I don't know. Like I was just thinking that it like makes sense. If we did 315 over 50 is equal to x over or 1,000 over x, and then we would get what the number is.
Why don't you try it and see? I don't know, to be honest. I don't think that does work in this problem. But there's always a chance that that works. But I don't see the proportion in this problem though. We're not given any information proportionally. So I'm not sure if that would work. I don't think it would.
Try.
Yeah, definitely.
I'm lost. Why don't we need
What are we trying to find in part A? What does it say? Read it. What? Which is rho, not m. We don't want m. We want rho. So we replace m with rho v, which is always one of our formulas. You have to memorize this by now. M is rho v always. So you replace m with rho v because we're looking for rho. But the problem is, Gavin, we don't have v, the volume of the object. So we move to this formula to find the volume of the fluid that's been displaced, which is the same as the volume of the actual object. Simply because we know the density, the buoyant force of water right here. We know the density of water, and we know the gravitational constant. So we're using the information that we have to plug in and get a number. These are extremely difficult, and I'm doing this on purpose. I want you guys to see tough problems here. Okay? If you have like one problem to this difficulty level, sure, one problem.
This is almost ridiculous.
No, it's not. It's practice. That's all it is. A lot of people didn't do their homework, and I realized that. That homework assignment, there was a big homework assignment. It didn't seem like it, at least, when I went over it.
Last night I literally looked at the homework and I was the guy going.
All right, let's plug in here. The buoyant force in water is what?
50.
Good. The density is 1,000. And this is 9.8. I'm dropping units, obviously. What do you get? Erica?
0.005.
Good. Meters per second.
Just kidding.
It's not velocity, it's volume. Thank you. Common mistake. Common mistake. That V. All right. So we have the volume of the fluid displaced, which means it's the same as the volume of the object. So now watch what I'm going to do. Take this formula, rewrite it down here. Okay, rewrite the formula down at the bottom, but now you know the volume of the object. I'll write it in blue. You don't have to mock me. Solve for rho, because we're looking for the density of the object. Solve for rho. Obviously, in form. The volume is the same again, yes. VF that we just got a minute ago, the volume of the fluid displaced is the volume of the object itself. Okay? So let's take FG over VOG from here by dividing this part over here on both sides. Now again, we know these values. We know the force of gravity is 315. We know the volume of the object now because it's the same as the volume of the fluid displaced. And we know G. Plug in. Stop whispering so much and write. I can't hear you. Shh.
I got 799.
What did you get? 799. Let me see what I got here. I didn't get that. I got
681.
Hadley, go ahead, Hadley.
6422.02.
I'm just going to say that, right?
I got that. Why did you put in?
You need parentheses around your denominator in your calculator.
Why do you have?
Bless you.
Steph?
Why do you have
315, force of gravity, the weight of the object.
Oh, I thought we were doing. We just plugged in the buoyant force.
We're going to do oil next in part B. This was part A. So guys, this is part A, the actual density of the object.
Why are we in honors?
This is only one problem that's tough, guys. The next few are much easier. You got to be challenged a little bit. You can do it. Relax. Relax, guys. You need to practice more. You need to practice more. I'm not going to lie.
I did it out loud.
Well, you know what?
This part.
I'm not going to lie. I'm not trying to be mean, but there were only 2 people at office hours. So if you got the homework, you should be getting this. This is actually easier than the homework. If you didn't get the homework, you should have been at office hours yesterday. I mean, at least make the effort. So don't complain, please. Let's look at part B. For part B, we want to find the density of the oil. Okay, the density of the oil. Now, what do we know about the oil? We know the force of buoyancy in oil. We had that from earlier. That was 40. Let's just write that down from earlier. We're trying to find the density of the oil. We know the volume of the fluid displaced, VF. It's going to be that same volume we had earlier for the object because it's still fully submerged. So that same number that we solved for a few steps ago that we used for the volume of the object, we're going to still use for the volume of the fluid now because the object is not changing. Now, think about what we know in this problem. Okay, think about what we know in this problem.
What are we trying to find?
We're trying to find the density of the oil, of the fluid. Write down your equation with buoyant force. What's your equation for buoyant force?
F equals MA.
FB equals? Okay, but what else? We also had another formula. Give me the other one.
FB equals
Good. Remember this one from earlier we used. We used this earlier on water. On water. We haven't used it yet on oil. Take a look. We know the force of buoyancy in oil. We know this number here. It's 40. We know the amount of volume of oil displaced. It's the same as the amount of volume of the actual object we got earlier. This from earlier. We know G. Rearrange it and just solve for rho F. Solve for the density of the oil. Okay, all you're doing is solving for it here, yeah. Mm-hmm. Yep. And that's not boil, it's FB of the oil, obviously. So don't confuse that. This is a capital V. It's tough to emphasize sometimes. Make sure you try to.
Really make it look like it's a P.
I did the first time.
What do you get for this?
Wait, is it 815 plus 49?
815 and a half.
Whoa.
Very good. Let's make sense of this now. Let's go back and make a simple conclusion for all of this. Let's make a conclusion. What was the density of the object? Answer the question. What was the density of the object? Erica.
6,422.0.
All right, 6422. Here's my conclusion I'm going to make. Ready? So the density of the object was 6422. Units are the same. Let's write it down. Hold on. The density of water itself, okay, is 1,000. And the density of the oil was what? What did we get there at the end?
815 and a half.
Which had the highest density? And didn't the object sink in both?
Yes.
Does that follow what we said earlier? That if an object's density is greater than the fluid, it sinks. Okay? Now, the buoyant force is different in oil and water. Which had a higher buoyant force? Oil or water? Water. Water was 50. Oil buoyant force was 40. Look at the density of water. That means water's density is higher than oil. It's able to push back more. So that's why its buoyant force was 50. The buoyant force from the oil was only 40 because it's not able to push back as much. Its density is lower. Okay? That's our conclusion we can make to make sense of the answer. It's what you need to do on the test. It's tough. But when you get an answer, some of you don't check it for what's called sanity. Sometimes you put answers down and I'm like, how is this a small car 6,534 newtons, like some ridiculously large force or something like that? It doesn't make sense, right? You start with a diameter of like 2 centimeters and the other diameter is 12 kilometers. It's like, that's not a pipe. You can't have a diameter of 12 kilometers. But sometimes you get those answers. So I'm trying to make you think back and make sense of your work. Helen. Quickly, Helen, because we have like a lot.
Oh, sorry. Is there a reason that the density of the object is like 8 times the density of oil? Or did that just happen? I think that's what you were getting at.
Probably because think about
That's probably
315 over 40 is about 8. 315 the weight over 40 the buoyant force is about 8.
Okay.
315 over 50.
Wait, so once we have tornado, we could.
Nah, it doesn't really hold true. 315 over 50 is about 7. Oh no, this is about 7 times that. 6.5 times. Yeah, I like that. So maybe the proportion does work. Check.
It
Check.
definitely does work.
Erica.
No, I got that before.
our conclusion is that water is more dense than oil?
Correct. That's why oil floats on water. Does everybody know that you put oil in water?
Yes.
Oil floats on top?
Dressing.
Yeah, because look, the density of oil is less than water.
That's what
And
it's
the portion I got 8.15.
Water is more. Water is more.
8.15?
No, 8.15.27.
That's awesome.
That's
Yeah,
how it works.
that's really awesome. I didn't even think about that. Nice, Helen.
Way to go, Hell.
So, Helen, can you make a statement?
Hell, make a statement. Look, we can name this the Helen Principle.
Okay, I guess. Okay, so the row of oil
Of the fluid.
is proportionally related to the row of the object.
Okay.
Okay.
But what's the fraction that needs to go in front now?
Oh, one
Someone's coming.
Oh, yeah.
Which was on? So which is the smaller one? Use your numbers that you told me a minute ago, Helen. Tell me if that makes sense to you.
Helen, you're really struggling.
This is what Helen was saying.
Okay, the PF is 1/8 PO.
Yeah, take a look, guys. This is actually really cool what she picked up on. Remember the overall weight was around 315? Okay? And if you put 40 up here, which was the buoyant force in oil, 40 over 315 is about 1/8. If you take 1/8 of the density of this object, you get almost this exact number. It's actually exact if you use the right numbers here. Same thing goes for water. If you use the buoyant force in water, which was 50 over 315, and multiply it by 6422, you'll get the 1,000
Do
there.
we have to know this?
No, but I didn't even realize that. That's something I didn't know. That's awesome.
Wait,
It's like a correlation for this problem.
That's a cumulative correlation.
No, it's not going to work for all problems, Helen. It's for this problem.
I
Okay?
told Helen that.
That's really good.
It's not going to work for all problems.
I'll let you take the credit.
Sir Isaac Tolan.
Actually, hold on. It might work for all problems.
I like the first cut, man.
Oh, but it's knees.
Yeah, try to like
Yeah. Mr. Howell, let's just carry on. It works.
It
Okay.
can work for all problems.
It works, I know.
All right, so I'm going to add it to the formula sheet.
Look at him, he's like, oh. Mr.
Very cool.
Mr. Howell, you know you have Sir Isaac Tolan in your class? But you just called yourself a boy.
Helen, you are a physicist.
You are a physicist.
Alright, let's get it going.
All right, cool. Very cool. Next question. 9-2. 9-2 is on pressure. So here's what I'm going to do, just to give you a heads up. Listen. Listen. I'm going to continue to record this, because we're not going to finish, obviously. Okay? I'm going to continue to record this on my own. And what you guys can do is, because you don't have class tomorrow, so you have from now until Monday just to watch the rest of the recording. And it'll go through all the answers for all these problems. Okay, we'll go through this one.
Will you be here after school on Monday for a little bit?
Sure?
Because we get out at 12:15.
Yeah, I have to do the sophomore interview at 1. So, about half an hour at least.
I
Yeah.
just want to like go over a few things.
All right.
Oh, they're like long.
What's that?
Software interviews are like long.
They're like 45 minutes.
That's fine. Whatever. It's cool.
No, I'm just saying.
Wait,
All
are
right.
you going to be my person?
You're not a senior, so I don't know.
No, but transfer student.
Oh, I don't know. I really don't know. I didn't look at it. All right, so the 4 tires of a car are inflated to a certain pressure. Each tire has a contact area with the ground of 0.045 square meters. Determine the weight of the car.
Alright, all listed.
We have pressure given right away.
Or not.
What's another given?
Area.
Area of what? 1 tire, right?
Oh, so area times 4 again.
We'll do that, yeah, at the end, but let's write 1 for now. I agree. Okay? What's our formula that relates pressure and weight? What is weight? Weight is a
Force.
force. So what's our force, pressure, area formula?
F equals P equals F over N.
Very good, Emmett. Okay? Guys, again, it's got to be, I mean, it's on your formula sheet, but if you did enough problems by now, you should have this memorized. All right, we're looking for what? The weight, which is the force, the weight of the object, the force of the object. And this is like F equals ma, but it's PA, and it's not A for acceleration, but A for area. Yep. How many tires do we have, people?
4.
Thank you.
That's our next one on the car.
Kudos.
How many do we have contacting the ground, people?
4.
There you go. Okay, you're going to get a force or a weight of the car. It turns out to be 540,000.
Yeah. Can you do 0.045 to 4 power? Can you do that?
Okay, numbers 2, 3, the rest of them will be recorded. You know what I may even do? I may record the others in the next class. And then they'll watch the beginning, you can watch the end.
Where did you guys find?
Do you have to divide it out?
Correction, 54,000.
It's not that much of a difference.
Just a factor of 10, right?
Yeah.
Take a minute to read it and list the givens on your paper. Take a minute to read and simply list the givens on your paper.
You got the pressure, 4 times the temperature. You got the radius, 0.003. And, yeah.
Anything else? Yeah, what are we looking for? F. Good. But remember, we have force, pressure, and area, but here we have force, pressure, and radius. So we're going to have to make some sort of a substitution, right? Okay? Good, Jeff. Pi r squared. So let's start. Here's our formula. You should probably have this memorized by now, even though it's given. You should probably have it memorized. Substitute for the area, pi r squared. Solve for F. Go ahead, Jeff.
Oh, yeah, I just solved. Okay, so you can just multiply by
Yep.
A, and then you switch A with pi squared.
The answer should be 100.
So you get for R.
Okay? That's really all this problem is here. But people don't realize right away what's going on because they see pressure and a pipe, so they think it's like an internal pressure. This is just like pressure, force, and area. That's all it is. Okay?
Would you want us to get the answer exactly or rounded?
Nearest tenth, I would always say. Nearest tenth.
But if you want, can we not use pi to give an exact answer?
Yes. An exact answer. Wait. Should you leave it in terms of pi? No. Give a number. Don't use pi. Don't leave it in terms of pi.
And you get 11.3.
Good.
11.3.
Okay. So the force that the bubble gum has to withstand is 11.3 newtons. Now, obviously, people, bubble gum you're not going to use, but an epoxy that you would put over a hole to seal something has to have a certain what's called tensile strength. It has to be greater than this number, or else what will happen? The water will rush through, it'll break through. Okay? So this is actually a good relationship or a good idea. The bubble gum idea is just a simple example. Right? Let's look at number 3. Take a minute, go.
For pi, we just put in 3.14.
I would just use the pi key on your calculator. There's a pi key on there. Okay. By the way, excuse yourself. I heard that. I mean,
I didn't think it'd be that loud.
0.025. It's 2.5 centimeters.
A meter.
all right. Why can I say this? Why can I say this to start right away? All right, guys, pause. I know you're working on it. I know you're working.
Yeah, they're all
Stash. Guys, stop talking. Stash.
Because you have the diameter up there.
Okay, but Stash, why can I write this as if P1 equals P2? That's not answering the question. Why can I write P1 equals P2? Yeah, Pascal's principle says the pressure throughout the fluid.
I thought you were asking why can't I just write out the code?
No, why can I write this?
Okay.
Okay. Now, let's list our givens. What do we know for this problem?
DA is 0.05 meter.
Good.
And DB is 0.25 meter.
Good. What else?
Well, I mean, I don't know where we do this with the object.
We know something else, people. What else do we know?
The object?
The object, which is FB or FA? B. Look at the location of it. Look at the diagram. And what are we trying to find? Okay, that is our givens, or those are our givens right there. Mash.
Why is it not FG for gravity?
It is, but I'm just calling it A and B, the locations. I'm using B and A for locations. They're not buoyancy, Masha. It's just location A, location B. In class, we used F1, F2, A1, A2. This is just A and B. Okay? All right, good. So our formula for Pascal's principle is P1 equals P2, which is just F over A for each.
Equals F over A.
And I'm going to call this A, and I'm going to call this one B. Whoops.
But you can do like 1 and 2, right?
Sure, you can do 1 and 2, absolutely. If A and B confuses you, use 1 and 2 for sure. Okay? Now, the problem is that we don't have the area, we have the... So what can we do? What's the formula for diameter?
You divide by 2, you get the radius.
And then squared, right?
Yeah.
So what's the formula become?
So it becomes
2 pi r.
It's normally pi r squared, right?
Yes.
But the radius is the diameter over 2, right?
Yes. So you square that.
So it's really just pi, these are r squared.
Isn't it easy just to do that in the beginning though?
Doesn't matter, I'm just using what's given. Doesn't matter. A lot of applications of engineering use diameters, not radii. A lot use diameters. Okay? I'm just giving you a heads up, so it doesn't matter. Either way, at this point in time, this is why I didn't do anything. Watch, folks. It's on both sides of the equation. What can you do?
Cancel it out. Pi.
Yeah, all those pi's and 2's cancel.
Oh, you can
Okay?
just leave the 2s.
Believe it or not, you can cancel inside the parentheses simply because both parentheses are being squared. That's why.
Why is it the pi that's canceled though?
Think about it. If there was pi in the numerator of both sides, they cancel, don't they?
Yeah.
So it's the same as having pi in the denominator of both sides. They cancel also. The 2 is in the denominator inside the fraction, which is being squared on both sides. So it can also be canceled. Simply because of that symmetry. That's why. So what does the relationship become? This is what I wanted you to see, Fernando. This is why I didn't plug in. Look at the relationship you get. That's what you end up getting. Which is the exact same thing we got the other day when we were given the radius. Do you remember? We used the radius the other day when we had AV equals AV with the continuity equation. And we plugged in for A, pi r squared on both sides. The pi's canceled, just like the pi's canceled here. And we had a fact that they were squared. They're still squared here, even with the diameter. Okay? Same answer with the radius. Same answer with the radius. What do you get?
You get 0.025 on the bottom.
What are we solving for? What do you get when you solve?
Oh, well, you're trying to find F2.
What are you calling it?
F1, I'm sorry.
It's 0.25, not 0.02.
Guys, are we finding FB or FA in this problem?
That was 0.02.
FB. Or no, FA.
0.25.
FA?
It's on the B.
Look up. What has the question mark? FA, right?
Yeah.
dB is 0.25.
Let's all plug in here.
No, yeah, no, but I'm doing... I did it wrong. I'm doing 0.25 squared.
Oh, yeah, that's right.
That's 0.05.
So move DA squared up. Move DA squared up here.
We just do proportional or cross multiply.
Okay, move DA squared up here and you solve for A. Plug in your numbers, you'll get the force A. Should it be less than the weight of the car or more than the weight of the car? Less. So there's a mechanical advantage, right? Oh, so it wouldn't make sense. I got 20. I didn't see any calculator motion there.
Divided by 0.065. Yeah, 20.
Okay? A 500 Newton car only requires 20 newtons of force. Great mechanical advantage. 1 to 25 ratio in mechanical advantage. So you probably have to pump it 25 times to move it the same distance as one pump. You know what I'm saying? Remember that we talked about? The drawback of mechanical advantages? Alright, let's go on to the next page. Number 4 in this section. Number 4. We got 3 more problems to go. Let's do it. Take a minute, go. I paused. All right, Tyson, give me one of the givens. Give me one.
Was the salt water?
I gave that. You give me another one.
The distance, 200 meters.
Good. So let's write H equals 200 meters. Because remember, this is underwater, and our formula has H in it.
Wait, I thought that was V.
The density of salt water.
That's not volume.
Look at the units, Jeff.
Oh, yeah, meters.
Isn't it nice though that you can say that now, right? Look at the units and you pick up on that. That's what you have to do.
Pick up on what?
Like that H is automatically a depth because it's meters. It's not cubic meters, so it's not volume. So we have those two values. If we want to find the overall pressure felt by an object underwater, what formula should we use from your notes?
FB equals FG.
What is it?
FB equals FG.
Not FB equals FG.
Oh, sorry. FB minus.
Nope. Raise your hand, guys. Others. What formula are we going to use? Pressure. You're not looking at buoyant force. Find the pressure on an object submerged deep underwater. Nope. Raise your hand, Jeff. I said raise your hand. Nope. It's not a net. Molly?
Is it density of the fluid times height times gravity?
Close. You're close. What's the whole formula, Molly?
Oh, plus P equals the pressure of the object plus...
Absolute pressure. The pressure of the air, remember? On top of the water?
Is it PO?
PO.
Okay.
It's called the absolute pressure. I know it's
and then plus...
atmospheric, sorry.
Plus density, height, and gravity.
Good. Okay? This is our formula we're going to use. Remember PO? That's the amount of pressure that the air has on the water. The amount of pressure that the water has on the object is this part right here. Okay? So this is the air pressure on top of the water. This is the water pressure on top of the object. The sum of those two is the total pressure felt by the object. Okay? Stop. It's called superposition, this principle. It's called superposition when you can add two quantities that are acting in the same direction like that. Now, P0 is always the same. I gave you that number. 1 times 10 to the 5 Pascals. That's also known as 1 atmosphere, and it's the pressure of the atmosphere on top.
That's not 1.29. That's the density, right, Bear?
The density over here is 1025, Jeff.
No, the density of air, 1.29.
Where do you see density?
I'm just saying, don't we? Oh.
Jeff, where do you see density?
Don't you want to find out
Read the problem. What does it say to find out?
Everything.
The pressure, which is capital P. So what's...
Look, my Dragon Ball. Help me go.
Wait, it's a girl or a boy?
Wally's obviously a boy, otherwise he'd be hanging.
Guys, you're not focusing. Stop talking about other stuff. So the absolute pressure on this object, the overall pressure that we're looking for, is a combination of the atmosphere weighing down on the water and the water weighing down on the object. The atmosphere always weighs down on you with the same exact pressure. This is a constant. It's on your formula sheet. Look at the bottom of it if you want to load it. The density of whatever the fluid is. We're in salt water. This is the density right here. The gravitational constant is right here. The depth into the water, H, is 200 meters. Add these two quantities together because they're going to have the same units. If you multiply these, you get pascals. Add those two numbers together to get the overall pressure felt by the object in pascals.
This makes so much sense. I feel like we overthink it.
That's what I got. Check your number.
I wish I could record all the things that Jeff says in every report. Simple, yeah.
2.1.
Times 10 to the 6. We can't move on until somebody confirms this.
I got that.
Molly?
That too.
Confirmed.
Fernando? We good? All right. So that's the overall pressure felt by the object. Remember, it's the sum of the air and the water together weighing down on you. The air is PO, the water is rho GH. Okay, if you need to write that down, you should write it down. Okay, that's what you should write. Air, water. All right, let's look at the next one. Take 1 minute to write down the givens. Section 9.3, the first one. Nasha.
So the volume is 2.7 times 10 to the -2.
I also got that.
That's the volume of the container, right? Awesome. What else? Cami. Do you know what that is in meters also? How many decimal spots do you remember for centi? Good. Okay. 2 decimal spots for centi. How about the time? What's the time, everybody?
28 seconds.
So some of you are like, yeah, we never used time. Sure, we didn't yet. But that doesn't mean you can't. Look at the continuity equation. What does the continuity equation say? Jeff?
A1, V1 equals A2, V2.
Yeah.
Fluid flowing in a pipe has a constant volumetric flow rate.
That's a lowercase v, by the way.
Velocity.
Okay. Jeff, nice and loud, one more time. Guys in the back, stop talking. Say what you said for the statement, not the equation. What was the statement?
A fluid flowing in a pipe has a constant volumetric flow rate.
Constant volumetric flow rate.
Oh.
Remember the other day we talked about this. We showed the units became meters cubed per second. Volume, meters cubed. Flow rate per second. So it's a constant. So it's volume over time, isn't it? Volumetric flow rate is volume over time. Would you agree?
Yeah.
So what we can say is the following. What we can say is this. The constant that we're looking for, AV, is equal to a volumetric flow rate, capital V over T. This is little v on the left here. Again, the volumetric flow rate is the volumetric flow rate. They're the same thing, written differently. That's why you're thinking outside the box here. We talked about how AV is a constant. What is it? It's this number. Whatever the amount of volume that was filled over the time period that it took to fill it. This is volumetric flow rate. So is this. We have everything. Substitute in for A with the diameter equation. What's the equation for the area of a circle when you have a diameter?
Pi d.
D over 2 times pi squared.
Said incorrectly.
Pi times d over 2 squared.
Thank you. Much better.
That's what? The area of...
That's an area of a circle.
This is the area of a circle using the radius as diameter over 2. The little v next to it is the velocity that we're trying to find. Okay, so this formula, we didn't really use this. We got rid of this part. Okay, and instead of putting that, we put v over t. And that's a capital V. This is volume. Okay, it's a capital V. Write the word volume if you have to indicate that it's not velocity so you don't confuse yourself. These are volumes.
Both V's.
Okay, the little v is velocity. That's what I'm trying to say. Look, Molly, up here. This is velocity. This is volume, okay? We are solving for
Velocity.
velocity. If I do this, it means you can kind of call it out. I like when you raise your hand. Thank you. But if you see me do that, it usually means that. So solving for little velocity. Let's take that whole expression and move it down below. I'm going to write the word volume so we don't get confused.
V on the left is still little v. Correct?
Yes, on the left it's still velocity, little v. So I took that entire expression, pi quantity d over 2 squared, and moved it down below by dividing through to get little v by itself. Okay, put your hand down, guys. Come on, let's go. Focus. You have a number for me? What do you got? Okay, get to it. That's what I'm getting at. So you don't have a number. Let's go. Units I know will be meters per second. because they're all standardized, and I'm looking for a velocity.
This is just like doesn't.
This is our continuity equation, right?
Yeah.
We have two quantities for these. That's this part here. We're looking for V, we have that because we have the D. But we have nothing about the rest of the pipe. We do know that it pumps out a certain amount of volume of water in a certain amount of time. Volume over time is the same thing as this, because this is called volumetric flow rate.
Only the second part though? What about the first part?
It's the same thing. It's just, yeah, think about it, Jeff.
So
if I replace it there,
should I not solve? I solve for the volumetric flow rate.
you could, that's fine. Yeah, you could put 9.64 there, that's fine. And then divide 9.64 by whatever this turns out to be. Sure. You could always do that, Jeff. Molly.
I got 3.07.
3.07. Did anybody get 3.07?
3.07 like 2, right?
If you did it that way, it would be 3.07.
Yeah.
3.069.
646. 306. 5288. That's my number.
Wait, maybe I did it wrong.
Are you? I could have done it.
I used the diameter. I didn't do diameter over 2 before I squared it, which is a huge difference. And I was wondering why my number was off. Did anybody else get this number? Raise your hand if you got this number. Don't lie, obviously. 1, 2. Okay, 3.069, yeah. You can round to 3.1 if it says nearest 10th on the test. All right, last problem. Last problem.
Good work, guys. Good work.
Take a minute to write it down, or to write down your givens. All right, given. What do we got? Given. Hands. Hands. Give me one piece, Olivier.
VA equals 2VB, I guess.
Do you guess or do you say?
I'm pretty sure.
You are correct. Again, make sense of this, people. Take a look. Take the words and make an equation from the words. It says the velocity at A is, so again, the velocity at A is, which is equals, twice the velocity at B. So you're just following along. That's all you're doing. Now, by what factor does the radius of the pipe change? Let's use the continuity equation again, because we're looking for radius and that has area in it. So aren't we really looking for RB, the new radius? Okay, we're looking for the new radius. So we can figure out by what factor does it change. The new radius. So continuity equation, go.
Since you have the radius, you can just do pi r squared.
Give me the continuity equation.
Oh, A equals AB.
Thank you.
And then you can substitute AB with pi r squared. Or sorry, A with pi r squared.
I got you.
Cancel out the pi.
Guys, why are you all talking under your breaths back there? Come on, focus. Get rid of the pies. Good, Jeff.
When is the situation where you can't get rid of the pies?
When there's a plus sign and they become addends. Right now they're factors, so you can.
And cancel out the
What else do we know? We have a given. What was the first given that Olivier told us? VA is twice VB. So replace VA with twice VB. There it is, twice VB right there.
And then you divide.
Again, take a look. Replace VA with twice VB, because that's given at the top. It's all variables. Substitution method. What's on both sides now?
R and VB.
VBs.
Thank you. Just VB. R is not on both sides. Okay.
Little B over there, sorry.
Thank you. Now we can solve for RB. Isn't that what we're trying to do?
Yeah.
By what factor is it going to go up? So we can solve for RB with RA in it. Let's take a look. How do you get rid of a square? Square root it. That's what RB is, if you take the square root. But what's the square root of RA squared? This is RA, so this is root 2 times RA. So by what factor does RB go up? What's the factor? Radical 2. Again, We start with the continuity equation. We then plug in for the formula for area as pi r squared. We realized that we had a given that VA was twice VB. Plug that in. Cancel VBs on both sides. Solve for RB by taking the square root. But the square root of a square is that quantity itself. The square root of 2 is the square root of 2. So by what factor is RB changing? Here's what you say. RB increases by a factor of radical 2. RB increases by a factor of radical 2. If it was over radical 2, if the answer was RA over radical 2, you would say RB increases by a factor, or decreases by a factor rather, of radical 2. But since we're multiplying by radical 2, RB increases by a factor of radical 2.